So the other difficult topic from Unit 1, or that seemed to give people issues, is moment or torque. I'm inevitably going to call it torque, so I wrote it up there, but you should call it moment. And that is the turning effect of a force around a pivot or a hinge. And the definition for it is quite simple. So the moment, it simply equals the force times the distance from the pivot or the hinge. And that should be the perpendicular distance. So I'll give you an example of what I mean. Okay, so this is the perpendicular distance. But just a note about units, remember, so force is measured in newtons. The distance is always measured in meters. Oops. And so moment is literally Newton meters. That's the unit. All right. Now, what do I mean by that? So if I have, for example, I don't know what that's supposed to be. It's a board magically bounced on a pivot point. But anyway, this is my pivot here. Okay. And so it's exerting a force this way, right? And so the idea is that the distance that you're measuring would be here. This is your perpendicular distance. It's at a 90-degree angle from the pivot. All right. So this is your distance. Trying to think of a better way to represent that, but I'm coming up a little short. One of the examples that I think you guys have done was there was a wrench that you were looking at. So there was a bolt here. You guys know I can't draw, so we're just going to pretend. And you had a wrench handle, and it was around the bolt. Okay, and so the idea is that this then is the pivot. And so the distance that you would measure is not this diagonal here. It would be directly out. You would want to measure the distance here. This is now your distance. So the first thing you want to make sure of when you're talking about moments is that you make sure that you're looking at the correct distance, the perpendicular distance from wherever. So if the force is being applied here, right, then you want to look at the distance there. And of course, this means that for moment, one of the basic ideas is that the larger the distance, the larger the moment, right? It's much, so if you think about a door opening, right, it's much easier to stop somebody from trying to open the door if you are if you're applying a force here than if you're applying a force here closer to the pivot, closer to the hinge. The other part of moments that you need to understand is the principle of moments. And the principle of moments, it states that if the moments on an object are balanced, then the object will not be in rotation. It will not be moving in any sort of rotation. And so let me get that written down. And so you need to remember that moments can, basically there's two directions that moments can act in, right? Clockwise or anti-clockwise. So for this, I'm going to take the example of a seesaw, right? And so the idea is that if you sit somebody over here, right, that person's weight is going to act here to the left of the pivot. And so that is going to be in the anti-clockwise. I call it the counterclockwise. It doesn't matter which one. Okay, the anti-clockwise moment, right? They're contributing over here, and a person on this side is going to contribute to the clockwise moment because it's moving. Just think about how the hands of a clock move, right? So this would be the clockwise moment. Now, and so if you wanted to figure out, is this oh, sorry, I forgot up here, the sum of it. So if this is true, the principle of moments, then then the object is balanced. Sorry, forgot to write that up. If you ever are asked to write the principle of moments, you should include that. Okay, now back to my seesaw example. So the idea is, let's say that this person look like they're a little further away. So let's say that this distance is 1 meter, and here this is just 0.8 meters. Okay, so 80 centimeters. And so then the person here could be 20 kilograms, and let's say this person here is 25 kilograms. All right, so the first thing you would have to do is find the force. All right, so let's do the anti-clockwise first. So let's look at the anti-clockwise moment, right? So it's going to be force times the distance. So the perpendicular distance. So here, please remember, right? This is their mass. So their force, their weight is going to be this times 10 because remember that weight equals mass times g. All right. We're assuming the seesaw is on Earth. I didn't state that, but I think it's safe to assume. I don't know if seesaws on other planets. So you have mass times g, right? So the force here is actually going to be 250 times 0.8. All right, so that's your anti-clockwise moment. And then your clockwise moment is going to be the force, which again, this person weighs 20 kilograms, so the force is going to be 200 newtons times 1. All right, now I'm going to do some quick math. And so the moment clockwise is going to be 200. That one's obvious. 250 times 0.8. When I was making these numbers up, I'm so proud of myself. I guess correctly is also 200. So for both of these, it's 200 Newton meters, which means the seesaw is actually in balance and nobody's going anywhere. So it's not going to go one way or the other. All right, as long as they're just sitting there. Obviously, if they push on things, that's different. That increases forces. So this is the principle of moments, and this is usually what students get confused by, rather than the basic basic idea or equation itself. That equation that I gave you, wherever it is, yes, please remember you do have to have it memorized. It is not given to you. It is, however, only in paper 2, right? So moment and momentum as well. They're both only in paper 2.